Welcome to the webinar Fundamentals of Neural Networks. My name is Primož Potočnik. I'm assistant professor at the University of Ljubljana, Faculty of Mechanical Engineering. And in this webinar, we will introduce the teaching package with modular contents for the introduction of the fundamentals of neural networks. And this package was prepared in collaboration with MathWorks Academia team. In this first chapter, we will just briefly introduce the contents and instructions about the package. It consists of a series of MATLAB Live Scripts and complementary PowerPoint presentations. So it is intended to guide the students toward basic understanding of neural networks, and it is addressed toward undergraduate courses, but can be also integrated with various postgraduate AI-based courses. The package can be downloaded either on GitHub platform or MATLAB File Exchange, and on MATLAB File Exchange you can also find the link to open the package directly in MATLAB Online. The contents of the package are organized in various folders, and the folders include PowerPoint files with some theoretical backgrounds and live scripts with practical examples. The teaching materials can be followed either through live scripts or through PowerPoint presentations. So the live scripts will provide some activities and exercises and practical examples, and they also contain link to complementary PowerPoint presentation, and PowerPoint presentations provide some theoretical background and also links to complementary live script examples. The learning goals include the introduction of the principles and methods of neural networks. We present some principal neural networks and demonstrate the process of applying neural networks. We also explain the most common neural architectures, and we develop the ability to construct neural networks for solving some real-world problems. Finally, there are some useful additional resources such as MATLAB On-Ramp course, Machine Learning On-Ramp, and Deep Learning On-Ramp. There are also some educator resources. And finally, if you have further questions, you can always contact MathWorks online teaching team. In this chapter, we introduce a neuron model and basic neural architectures. If we take a look at a neuron model, which is a very simple approximation of biological neurons, we can find the input vector, and then the neuron includes the weight vector and bias, and then we have the activation potential. Finally, there is an activation function such as sigmoid or radial basis function, and we get to the neuron output. If we combine such simple neurons into layers, then we can get a network of neurons, which is already artificial neural network. With respect to network architectures, there are various possibilities, such as single-layer feed-forward networks, multi-layer feed-forward networks, or recurrent networks. Let's take a look at these examples. This is a single-layer feed-forward network containing just one layer of neurons. The next possibility is a multi-layer feed-forward network, which is capable of modeling much more complexity. And finally, there is also a recurrent network, such as the example below, with several feedback connections, which is suitable for dynamic processing. And we also have to distinguish between learning algorithms and learning paradigms. The learning algorithm is a prescribed set of defined rules for the solution of a learning problem, such as error correction learning or memory-based learning. And the learning paradigm is a manner in which a neural network relates to the environment, such as supervised learning, unsupervised learning, or reinforcement learning. This chapter concludes with two MATLAB Live Script examples, and we'll take a look at the first one, which is simulation of neuron output. This first live script presents an example of a simple neuron output. The script can be run as with a run button, or run section by section, or run in advance. So first there is a short introduction, then we have illustration of the simple neuron, and then we can already define some neuron parameters, such as the weights, the bias, and we can also choose the activation function. And finally, we can calculate the neuron output for specific input as follows. So we now run this section, and let's see for the result. the neuron output is calculated as follows. And in the next step, we can see also how to calculate the neuron output over the range of inputs. We use the mesh grid command and calculate the neuron response over the complete field of inputs. We get the following nonlinear response, which is very characteristic for the neuron, which is used for neural networks. Finally, we can also construct a neuron already as a neural network. So we use the linear layer command, then we configure the network, define the transfer function, weights and bias, and we can already show this configuration, which is as follows. It is just one layer with one neuron, and if we calculate the response of this network to the input range, we get the same response as by previously manually calculating the neuron output. At the end of the live script, you have also the link to the associated PowerPoint presentation with some more theoretical background. In this chapter, we present Perceptron and Adaline. Perceptron neuron is a simple neuron with hard limiting activation function. Therefore, its output can be either 0 or 1, and as such, it is useful for classification. Perceptron neuron can be trained by perceptron learning rule, which starts with random initialization of connections, and then it's picking up inputs from the set of training samples, and based on the perceptron response, the connections of the neuron can be modified according to the learning rule. And this learning rule is proportional to the output error and the input signal. And then we are iterating this learning rule until all the inputs are correctly classified. If we combine several perceptron neurons into a single layer, we can compose the perceptron network, which is already a useful architecture to classify in more than two linearly separable classes. The next element is Adaline. It is adaptive linear element, which is also a simple neuron but with linear activation function. And Adaline can be trained by LMS algorithm, that's least mean square learning rule proposed by Widrow and Hoff. And it's an important generalization of perceptron learning rule because it additionally introduces the learning rate to regulate the learning process. If we compare Adaline and perceptron, they are both simple neurons, and Adaline has linear and perceptron non-linear hard limiting activation function. They are also both trained by similar learning algorithms, but the LMS learning for Adaline additionally introduces the learning rate. And they are both useful for approximated linear input-output mappings. But unfortunately, this type of structures are not useful for solving the nonlinear problems such as simple exclusive OR problem, and we'll see in the next chapter on backpropagation how this problem can be addressed. But in this chapter, we have a few more live script examples, and we'll take a look at the perceptron and perceptron network example. In this example, we demonstrate classification of linearly separable data with a perceptron. As first, we define some input and output data. So we generate two clusters of data. We can define here the number of samples in each cluster and the distance between the two clusters. And these two clusters of data belong to two classes. And so we also define the outputs. We define zeros for the first class and ones for the second class. And with this data, we can train the perceptron. First, we create the perceptron with a perceptron command, as shown here, and then we can train it by train command. Then we can also visualize the architecture of the trained perceptron, and finally we use this trained perceptron to draw the decision boundary between the two classes of data, and we can see that our perceptron successfully solved this classification task. In this example, we demonstrate application of a perceptron network for classification of a 4-class problem. As first, we define some data. We generate 4 clusters of input points in 2-dimensional space, and these data are belonging to 4 classes, A, B, C, and D. And for the output coding to train our perceptron network, we define outputs as follows, as shown here. class A is encoded as 0, 1, class B as 1, 1, and so on. And with this we can then create a perceptron and train it. And for training we apply here the adapt command for adaptive training in order to be able to visualize the training process. It shows that if we replay the training, we can see that there are two decision boundaries, and we have actually two perceptrons distinguishing the input space, one in the vertical and one in the horizontal plane. And combined we have the classifier which is capable of classifying 4 classes. We can also here visualize the perceptron network. We have 2 neurons with hard limiting activation functions. And finally, how we can use such a trained perceptron network. We can randomly pick an input point with this slider here. So we have here is our input point. And then we apply the perceptron to receive the output. And we get the following response. Our perceptron network response is 0, 1, and now we have to decode this response. And with respect to our output coding, we can see here that 0, 1 belongs to class A. Therefore, we can say that the perceptron network correctly classifies the input as belonging to class A. So this completes the example on perceptron network, and at the end there is also a link to the PowerPoint presentation. In this chapter we will discuss backpropagation, which is a central topic for artificial neural networks. We will take a look at multilayer feed-forward networks, which is an important class of neural networks, also commonly referred to as multilayer perceptrons. And this type of neural networks can be trained by backpropagation learning rule. So this rule consists of 2 passes of computation through the network. First we have forward pass, where the input is applied to the network and then propagated to the output, and finally the error signal is calculated. Then in the backward pass, the error signal is propagated backwards, error gradients are calculated, and finally synaptic weights are adjusted. To work efficiently with backpropagation, usually some kind of fine-tuning is required, such as choosing the proper training mode, activation function, learning rate, momentum, defining some stopping criteria, and there are also heuristics for efficient backpropagation and some methods to improve generalization. Generalization is very important for neural networks, so we require that they compute the proper response also for some new testing data. Figures below show examples of overfitting and good generalization. There are some ways to improve generalization, such as keeping the network small, early stopping, regularization, and early stopping, as shown below, is a typical example of training neural networks. So we divide the data into the training set, validation set, and test set in order to properly train the network. There are also some advanced algorithms, such as variable learning rate, resilient backpropagation, Levenger-Marquardt, and conjugate gradients, and below you can see the MATLAB training functions for this type of algorithms. This chapter concludes with several live script examples, and we'll take a look at the first one using the multilayer perceptron for exclusive OR problem, and an example of industrial diagnostics using also the principal components analysis. In this live script example, we construct a multilayer perceptron for solving the exclusive OR problem. First, we define 4 clusters of input data, as shown below. We can here define how many samples will be in each cluster and the offset between classes. And we get this result. We have class A samples and class B samples, and they are not linearly separable, so we need a non-linear classifier if we want to solve the task. So for this we define a neural network, and as first we prepare the inputs and outputs for network training. We define outputs as -1 for class A and 1 for class B, and then we create and train a multilayer perceptron. Here you can see you can define the number of neurons in the first and in the second hidden layer. Then we use the feed-forward command to create a neural network. We also define some training parameters, such as ratio between training validation and test set data. And finally, we train a neural network with a train command. Let's see the results. Here is the picture of our network with two hidden layers, and we can calculate the efficiency of the network, so-called the network performance, as a classification accuracy. That's just the number of correct predictions with respect to total number of predictions. In this simulation, we get the 100% correct response. And if we plot the network response and the targets, we can see here the -1 and 1. So in this case, we get all correct predictions. And finally, we can also plot the classification result now for the complete input space. So if we have here all the input space, you can see how the neural network defines the classification boundaries. So the areas here belong to class B, and here is the class A area, and the network correctly classifies all the data. At the end, you have also some suggestions to experiment with network configurations and parameters, and also the link to the associated PowerPoint presentation. In this example, we apply a multi-layer perceptron and principal components analysis for industrial diagnostics of compressor connection rod defects. So we are considering here some industrial data. The pictures below show compressor head and the connection rod, where you can see already a crack which appeared during the imprinting operation. So the industrial data includes the measured forces during the imprinting operation. So we load first this industrial data. We have forces, 2000 samples, and then also the labels for each measured force, which is either OK, overload, or crack. And for this example, we simplified this, and we consider only two classes, either OK or defect. If we plot all the measured forces, we get the following result. These are forces for normal compressors, and these are all the defected operations, either overload or crack. So now in the next step, we want to reduce the dimensionality of the data, and we apply principal components analysis to reduce the data. So we load all the forces, we standardize the forces, and then we apply the PCA command to calculate the principal components. And then we can plot the variance explained by all these principal components. And we can see from the graph below that already the first and the second principal component combined, they explain already more than 50% of the variance. So now we use only these two components to plot our data. We get the following result. So you see here is the cluster of normal operations, and scattered around are not normal operations. Now we want to train the neural network. We define the output coding. 0 is OK and 1 is defect. And then we create and train the multi-layer perceptron. We use just one hidden layer of neurons as we define it here. Then we construct the network with feed-forward, and then we train the network. This is how the structure looks like. And when we evaluate the network performance, we get like about 99% correct classification. And if we plot classification now in the range of first and second principal component, we get the following decision boundary, which quite nicely classifies all the input space and efficiently solved the industrial task. At the end, you have also the links to the PowerPoint presentations on this topic. In this chapter, we introduce dynamic networks because time is quite an important ingredient for various learning processes such as speech, vision, signal processing, control, and we can build time into the operation of neural networks either by adding temporal memory or feedback. Memory can be implemented as a long-term memory, as the synaptic weights in the static networks, or short-term memory, which adds the dynamic element to the neural networks. The tap delay line is the simplest form of short-term memory, and it consists of unit delay operators to add some dynamic component. With this we can already build focus time delay neural network, and if we delay also internal layers, we get into the distributed time delay neural network. The next one is the layer recurrent neural network with some internal feedback between the layers. And the final one is the NARCS neural network, the nonlinear autoregressive network with exogenous inputs, which is a very powerful structure. And for the NARCS training considerations, we can use actually so-called series parallel architecture, which is simplified for training. And then for the operation, we apply the proper parallel architecture, which is the original NARCS network. In summary, we have several possibilities for dynamic networks, such as focus time delay neural network, distributed time delay neural network, layer recurrent network, and NARCS network. And in this chapter, we will also show the example, the NAR network for recursive prediction of chaotic Mackay glass time series. In this example, we demonstrate the application of a nonlinear autoregressive neural network for prediction of chaotic time series data. As first we generate the data, here you can see the Mackay glass time series, and we can define how many training and validation samples we will generate. Here is some mathematics to generate the data, and this is our data. So this is our training data, and this will be used for the validation data. Now we configure the NAR network. We have to define the number of neurons in the first and in the second hidden layer. And now, because we have a dynamic network, we also have to define the number of input delays and the delay step. So this is definition of the neural network. Now we have to prepare inputs and targets for a dynamic training with some commands here, and then we train the NAR network. We use the train command here, and we have now the structure of our network, and the final step would be to transform the network from the training, which was the series parallel architecture, into the operational parallel architecture. So now this figure below shows already the proper nonlinear autoregressive network with global feedback, and we use this network for recursive prediction on validation data. This is the final result. So you see we had here now the training data, and for the validation we start to predict here recursively from this point from 300 on, and there is a kind of increasing output error, which is obvious due to the chaotic properties of the training data. So this example demonstrates the dynamic network, and you have at the end also the link to the PowerPoint presentation. Now we present radial basis function networks, which are feed-forward networks with two computation layers. First, we have a hidden layer, which implements radial basis functions, and then the linear output layer. In MATLAB, we can represent RBF neuron as follows, and then with such neurons, we can construct radial basis function networks consisting of a RBF layer and then the output linear layer. For the RBFN training, we can use either exact interpolation with regularization or supervised RBFN training, or a two-stage hybrid training, which is very fast. So we have hidden layer training with methods such as k-mean clustering or others, and then the linear matrix operation for the output training. If we compare the RBFN networks with multi-layer perceptrons, they're a kind of similar feed-forward networks. They're both universal approximators and can be also used in similar areas. But for the multi-layer perceptrons, we usually use sigmoidal units, and for the RBFN networks, the radial basis function neurons. Then we have the family of probabilistic networks, which is also based on RBFN networks. This is used for classification problems. And first we have the layer of radial basis functions, and then the competitive output layer for classification. And the last structure is generalized regression neural network, GRNN, and it consists of a standard radial basis function layer, then the linear layer, but we also have the normalization layer, which makes the GRNN predictor quite a robust structure. In summary, so we have RBFN, PNN and GRNN structures. And we will also present two live script examples, namely RBFN structures for function approximation and for classification. This example demonstrates application of radial basis function networks for function approximation. As first we generate some training data. We generate a nonlinear function, but just in two segments, and there is some noise added to the data. And when we have this data, then we try to fit various models for function approximation. The first one is simple linear regression. We use the neural network constructor feedforward net, but without any hidden layers, in order to receive just one linear layer, which resembles the linear regression. And this is the result. We just have the linear approximation to our nonlinear underlying data. The next model is exact radial basis function network. Here we define just the spread parameter, and all the data, in our case 500 points, are used as centers of the radial basis function network. We receive the following result, which is a quite good function approximation to the noisy data with good generalization, but not very meaningful extrapolation or interpolation. The next model is improved radial basis function network. Here, beside the spread parameter, we also define the maximum number of neurons as follows. So we have the network with reduced number of neurons, and the result is as follows. We receive also a similar, quite good function approximation, but again not so meaningful extrapolation. And the next model is generalized regression neural network, which is quite robust predictor. We just have to define the spread parameter here, and the result is as follows, which provides, beside the good function approximation, also quite meaningful and robust extrapolation and interpolation. As the final model, we define also multilayer perceptron just for comparison. We define two hidden layers of neurons, and we have the following result, which is somehow similar to the operation of radial basis function networks, which also confirms that these two types of networks are applicable to similar application areas and can yield also quite similar results. At the end, you have also the link to the PowerPoint presentation. This example presents application of radial basis function networks for classification of an exclusive OR problem. As first, we generate some data. We generate 4 clusters of data belonging to 2 classes. We have class A and class B data, and then we define the output coding. A is -1 and B is 1, and as we can see, the 2 classes are not linearly separable, so we need to define nonlinear classifiers. As first one, we construct the exact radial basis function network. We have to define the spread parameter, then we train the network, and the result is as follows. We get a correct classification of the input space, but somehow interesting decision boundaries. The next model we fit is improved radial basis function. In this case, we use only 50 neurons. We can define the number of neurons here, and after the training we get the following result. We receive correct classification of the input space with somehow more smooth decision boundaries. The next structure is probabilistic neural network. Also here we just define the spread parameter, and after the training we get quite smooth decision space with correct classification. And the next one is generalized regression neural network. Also here the spread parameter, and after training we receive a very smooth classification result. So we have in this case like very robust classification model. The last structure is improved radial basis function combined with Bayesian regularization. We define in this case just 30 neurons, then we train the network, and we get the following result, which provides a correct classification. And we can also see that in this case the RBFN centers are not anymore positioned on the training data, so we have some supervised learning to optimize the network structure as well. At the end, you have also the link to the PowerPoint presentation and the plotting functions which were used in this example. In this chapter, we introduce self-organization and self-organizing maps. Self-organization is a very interesting phenomena where the system structure appears without some pressure or involvement from outside of the system. And constraints on the forum are internal to the system and are resulting only from interactions among the components. This self-organization can evolve either in time or space, can be stable, or can also show some transient phenomena. And an example below shows an interesting emergence of self-organization in yogurt lids by just shaking this structure. In neural networks, self-organization can be accomplished through competitive learning. So we have the neurons in the network which compete to be activated, and only one neuron becomes a winning neuron. The implementation of self-organization neural networks can be accomplished through self-organizing maps or through learning vector quantization. We'll take a look at the Cohonen network, which is a classical example of self-organization. It is based on the paper published by Cohonen 4 decades ago. So we have this Cohonen network, or also called self-organizing map, which has a single computation layer, and it is arranged in either 1, 2, or 3-dimensional structure, as shown below, and all the neurons are fully connected to the inputs. The SOM architecture can be also represented as follows. First, we have calculation of the distances between the inputs and the neurons in the SOM structure, and then we have a competitive layer which is selecting the winning neuron and its neighborhood based on some distance metric, and the topologies can be either 1, 2, or 3-dimensional. Let's take a look at the SOM algorithm briefly. It starts with some initialization, which is random picking values for the weight vectors. Then we have sampling of inputs from this input space, and then several steps of competition, cooperation, and adaptation. Competition picks the winning neuron. This is the one which has weights closest to the input vector. Then we have cooperation, which selects neurons which are in the topological neighborhood of the winning neuron. And then adaptation, which adapts the synaptic weights of the winning neuron and also his neighbors. And we have iteration of these 3 steps until the feature map converges to some final solution. Let's take a look at a few examples. First one, we have here the 2-dimensional data distribution, and we are fitting 1-dimensional SOM network into this data. So you can see the initial condition, and then at the end of the ordering phase and the end of convergence phase, which presents how the 1-dimensional structure properly represents the 2-dimensional input data. The next example is fitting the 2-dimensional SOM network into this 2-dimensional input data. So we have this first initial condition, and then the end of the ordering phase and end of convergence phase, which also adds some fine-tuning of this SOM network to the distribution of the input data. The final example shows the uniform distribution, in this case in a circle, and we are fitting the 1-dimensional SOM network and 2-dimensional SOM network into this data, and you can see the results, how both structures somehow try to represent the input data. This chapter concludes with a MATLAB Live Script example, which is constructing the 1-dimensional and 2-dimensional SOM structures to represent the 2-dimensional input space. This example demonstrates the application of 1-dimensional and 2-dimensional self-organizing maps to represent the 2-dimensional input space. First, we create some input data. Here we can see we have 4 clusters of input data, which represents slightly challenging problem for self-organization, and we have no output data. And then we try to create and train 1-dimensional SOM network. We have to define some network parameters, such as SOM dimensions. This is the number of neurons in this one-dimensional SOM network. Then the topology function. We select here hex topology and the Euclidean distance function. There are also some training parameters, such as initial neighborhood size and the number of initial covering steps. Then we can use the self-org-map function in MATLAB and train this network. And let's see the result. After training, we get to the following network structure and our result. We can see here how the one-dimensional SOM network tries to cover all the input space and to represent its statistical distribution. In the next step, we create and train the two-dimensional SOM network. Here we have to define the topology in 2 dimensions, so we have 10 times 10 neurons in this SOM network. In this case, we use the grid topology and Manhattan distance, and after training we get to the following network structure and the result covering the input space. We can see here how the 2-dimensional SOM structures tries to fit to the original input data. We can add also some other visualizations, such as plotting the neighborhood distances. We can see that this somehow corresponds to the above plot of some weight positions. And finally also some statistics, which shows the number of input vectors that are classified by each SOM neuron. So this concludes our example, and at the end we have also the link to the PowerPoint presentation. In this last chapter, we discuss some practical considerations on training and applying neural networks. If we take a look at the general AI workflow, we start with data preparation. We have to properly access the data and apply some pre-processing. Then we are training the network model. We have to properly design the model, choose the architecture, and tune properly hyperparameters. And finally, we deploy the system on various platforms, on application and enterprise environments. The first step is preparing data, because in practice neural networks give generally poor results if we are applying the raw input data. Therefore, for most applications, some data pre-processing is recommended, such as preparing data, which means designing the training data, handling missing data and outliers, incorporating invariances and some prior knowledge. Then we have to properly prepare the inputs, which means some kind of pre-processing, rescaling, normalizing, standardizing, also detrending for time series data. Dimensionality reduction is very important. We can apply principal components analysis or feature selection and feature extraction. We also have to properly prepare outputs, such as encoding the classics and some post-processing. Neural nets are also very useful for dimensionality reduction. So we can use the multilayer feed-forward neural network to perform dimensionality reduction in the form of auto-associative multilayer perceptron, so-called autoencoder. It has some extra hidden layers, and these ones can perform general nonlinear dimensionality reduction. If we see the picture below, we are mapping the picture from the input to the output. And we have several layers, and the bottleneck layer in the middle, which performs the nonlinear dimensionality reduction, which can be useful for neural network applications as well. The next very important topic is generalization, where the goal of our training is that the neural network will build a statistical model that generates the data, not just fitting the data. So a well-trained network is capable of generalizing well, which means making good predictions also on new data. The figures below show examples of good generalization and overfitting. With respect to generalization, we can talk about underfitting and overfitting. Underfitting is actually when neural network is unable to properly learn the data due to too small number of neurons, or maybe due to extreme regularization. And such network also doesn't give good generalization. And overfitting is when neural network perfectly learns all the training data but gives poor results on some validation or test data. Figures below show the underfitting and overfitting in function approximation. There are some ways to improve generalizations. First, how to prevent underfitting. we need to provide enough hidden neurons, which means to represent the required mappings properly. And then we have to train the network for long enough so that the output error is minimized. And we also can prevent overfitting by designing first the training data properly, then applying methods such as cross-validation, so we are checking ability of the network on some unseen data. We can apply early stopping before we come to overfitting, or restricting the number of adjustable parameters, either by reducing the number of hidden neurons or forcing connections to have some shared weights. We can also add regularization in order to make more smooth mapping of the network, or adding some noise, which also improves generalization. We have also some general guidelines for designing successful neural network applications. As first, we need to understand and specify the problem properly. And then we have to acquire and analyze data, define inputs, outputs, cleaning the data, removing outliers, applying some pre-processing, and then extracting features, selecting features, and properly encoding outputs. We also have decided about the network architecture, which neural network type, the network complexity, the hyperparameters, and the good start is to go first with simple neural network architectures, just with few layers and few neurons. Then we train the network, and we have to make sure that it's successful on the training data and also on validation data. And if that doesn't work, we have then to go to increase the complexity or changing the network hyperparameters. Finally, we have to test the generalization ability of the network to checking its performance on some new data. And if that's not successful, we have to go back and checking the data, partitioning of the data, and maybe changing the network architecture. Then we have deployment, which is the final step. First, we had this neural network design and training, application design. Then we have the deployment in the integration test environment, and then some real-time testing in the application environment. And then we finally also integrate analytics with our systems, which means fusing the data insights into workflows and applications. And this should enable the employees and customers to make more successful decisions. With this, we conclude our webinar, and I wish to thank you for participating in the curriculum Fundamentals of Neural Networks.